I will speak about what we know about concerning the future of Greenland and Antarctica, and because it's not so obvious. Everyone here says melting ice sheets, and actually the mass balance of ice sheets is not only melt, and one ice sheet can shrink without melting but going away in the sea. The work I will present is rather recent. It's a recent state of knowledge, and I want to acknowledge the program Ice to Sea, as Giorgio did this morning, which was a FP7 program during which a lot of improvements were done because we were a large enough number of groups to interact with each other, and I think it has been a qualitative jump in our knowledge thanks to this program. And you can find any information on the website. So, for the future, of course, I will speak about modeling because there are little way to do projections. I will not speak about statistical modeling, but process-based modeling. The processes involved in evolution of the ice sheets are surface mass balance, ice flow, but there are also some feedbacks and instabilities. I will speak a little bit about the models and their limitation, and I will make the point with some observation of the present state and how we use them for the projection. It will not be the outline because I will speak first of the Greenland and then of Antarctica. Here are the major processes that are involved in the evolution of an ice sheet. So, of course, the first thing that to have an ice sheet, you need to have snow that falls. And the snow that falls and melting on the edge at the surface are what we call the surface mass balance. But the equilibrium or the evolution of the ice sheet is completely governed by the ability of ice flow to evacuate snow that is falling in the central part of the ice sheet. This ice flow is ice is a fluid, very non-linear, and to calculate it, you also have to take into account that the fact that the viscosity depends on the stress itself, but also on the temperature. The typical temperature in an ice sheet is very cold at the surface and almost at the melting point at the bottom because you have geothermal heat flux warming from below. You have cold temperature at the surface coming from the fact that they are very high in altitude and geothermal heat flux warming from below. And sometimes you have basal melting, and this is another interaction with ice flow because sliding on the bedrock can occur only when the ice is at the melting point. So you also have this point, and even the water pressure can affect the way ice is flowing. And of course, it's a couplet problem because when you have ice flow, you bring frigories or calories, as you want, from cold from the surface and upstream to any location. So it is this whole system that is solved in ice sheet models, including a simplified way of doing isostatic response, because a change in thickness is about 1/3 has about 1/3 a corresponding change in position of the bedrock, and we cannot avoid it, but it is in a simplified way. So here I will focus on ice flow and a little bit on surface mass balance. I expected David to speak more about it. So to solve the equations, we have now a hierarchy of models without various approximation. On the previous picture, there were a huge exaggeration on the vertical dimension. If you had Antarctica over there, you would have a 3-meter wide sheet of ice and only 3 millimeters thick. So we take in many models we take advantage of this thin layer aspect to simplify some equations. So most models use thin layer approximations, but now we have a new generation of models that have a full resolution with the full Stokes equations. The ice flow strongly depends on the boundary condition, and the major boundary condition is basal drag. Ice is flowing under the gravity effort, but it is retained by the basal drag. And this basal drag can be due to the sediment properties. If you have a thin layer of sediment that is full of water, it will deform much easily than if you have hard rock. And it will depend also on basal hydrology. And of course, there are 3 kilometers of ice and no way to measure it. Here I have a sketch of how ice deform in an ice sheet. In the central part, ice deform mainly by vertical shearing in the vertical plane, while on the floating part, ice deform mainly by extending. And in the middle of the two, ice streams deform more or less ice streams that are very fast glaciers deform more or less like ice shelves, but with a basal drag. And you can get that we have trouble at the transition because the two approximations are not compatible. That's why, at first, full resolution model, full Stokes model have been developed. The second thing about ice sheet models is that they need a very small resolution. David spoke about 1 degree resolution for a GCM. In an ice sheet, it is now between 5 and 20 kilometers. One reason is that ice streams are a few kilometers wide. In Greenland, glaciers are really 4 or 5 kilometers. And of course, you cannot treat something like that is 5 kilometers wide with only 1 grid point. The other point is that on the edge of the Greenland ice sheet, the zone where there is ablation is very steep and very narrow, less than 20 kilometers. And this is one of the difficulties with the coupling with atmospheric model, because we have to find a way to make a match between the large grid of the atmospheric model and the small grid of ice sheets. Here is just an example of what I consider the state of the art as a model. It is a model that has been applied to the Greenland ice sheet for the next 200 years, and with a simulation for different surface mass balance scenario. And it is a full Stokes model that takes into account all the stresses, and you see that it has a non-regular grid that can be very small, close to for the glaciers. And this glacier specifically is a Jakobshavn icebreak. And it is well known because 20 years ago it was going 8 kilometers per year, and everyone was wondering, how does it go that fast? If at that time we had been told that now it is 14 kilometers per year, we would not have believed it. And that was why all the models improved a lot recently. It's because there were observations that were so stimulating, because we saw something that we didn't expect. So you see here the grid size is something like, I think it's 500 meters, not 1 kilometer. Of course, this type of model is very heavy, and it takes time, and it's no question now to do, for ensemble method with it. Now, the other point is the surface mass balance. There are two major components in the surface mass balance, and they have opposite response to warming. One is surface mass balance, it's precipitation and ablation. Ablation increases strongly with temperature. Well, it is what the common sense tells you. But precipitation rate increases also with a higher temperature. This is because, especially in the polar region, precipitation is strongly linked with the amount of water you can find in the air. When you have a warming, you have more moisture and more precipitation. But if it is really warm, then you will have rain in place of snow, and you go back. So you see, nothing is monotonous in surface mass balance as a function of temperature. So for Greenland, in case of warming, the central part is likely to grow a little bit because precipitation will increase, while the edges will be affected by ablation. In Antarctica, the coast of Antarctica is at about minus 10 degrees just now. So we are far from having ablation. There are a few patches of ablation in summer, but it is not substantial. So because there is almost no ablation at present, in case of a moderate warming, but moderate means less than 6 degrees, I would say, the surface mass balance is likely to increase. Of course, this is a very schematic point of view. With GCM, we see that there are also changes in the atmospheric circulation, especially because when you have a change in surface elevation, you have a different circulation and orogenic precipitation. And there is one point that is the polar amplification. When we are told this scenario gives, or this simulation gives 2 degrees of increase in temperature, it is likely that in Greenland it will be 4 degrees. This is for surface mass balance. So one could wonder, why do we have to have an ice sheet model? We could just cumulate what happens on the surface mass balance. So one thing is that if there is a feedback, if you have an increase in ablation, then you have a lowering of the surface of the ice sheet, and the lowering will extend the ablation area, and in turn will increase the lowering. So this feedback is the major reason to have to couple, or to at least to associate ice sheet models and atmospheric model. To evaluate the impact of this process, we did experiment in the framework of ISOC. So the experiment was like a Russian doll. We used 2 simulations by atmospheric ocean simulation by GCM to feed a regional atmospheric model that is MAR, which has a grid of 25 kilometers, more compatible with ice sheet evolution. And this, the results of this atmospheric model fed 6 different ice sheet models to evaluate the impact of the ice sheet models by themselves. The surface elevation was parameterized because not only these simulations were done on the present surface topography of the Greenland, but they were also done with different altitude of the Greenland ice sheet, and then it gave us a hint about how the surface mass balance changes with altitude. And with this parameterization, we did all the experiments with ice sheets. And actually, the results are here. Here are all the models. The cross is with no feedback, that just we take the surface mass balance given, changing with time, but given by the RCM. And the bar is the two ranges of the parameterization, and the dot in the middle is the mean value. First, one interesting thing is, except maybe a bit this one, but the models are fairly consistent between them. A funny thing is that in our lab we had 2 models participating, Grizzly that David told about, and Elmer Ice, which was the one I presented before, and we got exactly the same results, because in this simulation it was mainly the surface mass balance and the interaction with altitude that was important, and not the precise ice flow in ice streams. But you see that the difference between the two GCM that were used at the beginning to force the model gives them the larger uncertainty. However, this feedback is not important for the next century, neither for the century after, but it is not ruled out for a longer time. And if we had a more dramatic scenario, I remember this was for A1B scenario, which is almost equivalent to RCP 4.5, but with more dramatic scenario, maybe in 2 centuries, this feedback can play a role. And on long-term simulation, we see that this type of feedback can lead to a shrinking of the complete shrinking of the ice sheet. And it is often called instability of small ice sheets, because Greenland is a small ice sheet compared to Laurentide ice sheet, for instance. But it is also in paleo simulation, in experiments we did, it is also involved in the removal of the phenoscandinavian ice sheet. There are also dynamical processes, and one process is the calving. So we found out why the Jakobshavn glacier retreated. The reason was that the floating tongue was removed by warming of the ocean, likely warming of the ocean. And then, because the floating tongue was dragging on the side of the fjord, it had an effect on the ice flow upstream. And when the floating tongue was removed, the glacier was able to advance very fast. We still have trouble to model this type of thing. There are 2 studies done on this. One is to apply a flowline model, because it's easier to go to simulate a fjord with a flowline model that is very narrow than with a 3D model. And this study that was published very recently was done for the 4 major glaciers in Greenland. And then each flow line had a basin, and the influence of the outflow, the increased outflow due to calving for each basin was calculated. And the evaluation of contribution by the end of the century is between 40 to 85 millimeters. Unfortunately, they also tried to use the retreat of the glacier that gave this study to force the 3D model, and the numbers are much smaller. So it's quite difficult to know what we have to think about it. One thing is sure, is that the contribution stops when the glacier retreats enough to be no longer in connection with the ocean. So it is a very, very important process now. It's about half of the imbalance of the Greenland ice sheet now, but it may not last forever. A second process that is related to dynamical process things is the basal lubrication. The story is that in summer you have water at the surface of the ice sheet. We have the Greenland ice sheet is covered of small lakes, and this water can percolate in crevasses or moulins and reach the bottom, where it can enhance the sliding by lubricating the interface between ice and bedrock. This process indeed exists, and Roderick did a very nice experiment to evaluate the impact and to measure the water pressure at the base. But when put in the global model, it gives only small numbers. One of the reasons is that here again, it's not a monotonous process. When you have water going, reaching the bedrock, at the beginning, the water pressure increases, and then the ice accelerates. But it doesn't increase forever, because when the water pressure is high enough, a more efficient channelized water flow at the base develops, and this drains the water, and then the water pressure drops again. So during the season, you have an acceleration and a decrease again of the velocity. That's why, and it is one of the reasons why it's not that important for the global behavior of the ice sheet. So to summarize for the Greenland ice sheet, from the observation, we are about 0.7 millimeter per year, but it seems to be accelerating. For the future, the largest uncertainty comes from the spread of global climate models and from emission scenario. And I think without coupling and without doing ensemble simulations with a lot of models, it's the best way to estimate the future impact. Amplification linked to ice dynamics exists, and calving remains the most difficult point to predict. But with calving, it's a question of I must say that I'm skeptical about 85, but it's not huge numbers anyway. It's not as big as that have been predicted in previous studies. Now we jump to Antarctica, and here is a map of changes of surface elevation in Antarctica produced by Thomas Flamand in Lagos. In blue, you have places where the surface elevation goes down, and in warm colors where they go up. There is some thickening in all the plateau of East Antarctica, and it is attributed to an increase in precipitation rate, although we are still not sure that there are not densification processes involved in the signal we see in this type of study, because the radar, the altimeter, sees the surface of the snow, and with a warming, you don't know what happens to the fern and the fern layer that is 100 meters thick in the central part of Antarctica. But the striking point is that you see signature of things here and here, and a bit here and here, and these are outlet glaciers that are known to have accelerated recently. And especially in the Amundsen Sea sector, you see that the values are high. It's a bit saturated here, but the lowering of the surface is higher in absolute value than the accumulation rate in that places. So it's really an important process. And here we come with the nightmare of glaciologists, which is the marine ice sheet instability. Between the grounded ice and the floating one, there is the line between the two is called the grounding line. And the problem is that there is a topographical instability of this line, depending on the topographical characteristic of the bedrock. When the bedrock is deeper inland, for instance here or here, it's better, here or here, it is unstable. When the bedrock is higher inland, so here and here, the grounding line position is stable. So when if we take, for instance, this scenario where the grounding line is just at the top of a stable position, if there is a thinning for any reason, it can be basal melting below the ice shelf, it can be surface melt, it can be, or even if there is no, it can be that the ice shelf was grounded on some pinning points, and that the ice shelf melts and these pinning points are not pinning below the ice shelf anymore. Then the same as for the Jakobshavn Isbrae, the glacier, the ice shelf exerts a smaller force to the glacier upstream, and then the glacier can accelerate and lead to a thinning. But once you have a thinning, then you have a complete retreat until you find a new place where it is stable. And this is really a process that could affect quite a large part of Antarctica. It can be triggered by ocean, as I said, but it can be also triggered by a warming, atmospheric warming, because when you have surface melting, so I said in Antarctica there is no, but in summer on the ice shelves there is some. When there is ponding, the water of the ponds can go in the crevasses, and in the crevasses they open the crevasses when they freeze again. And this can break suddenly ice shelves. This happened to one or two ice shelves on the peninsula, and it is a very impressive process. In a few days, the ice shelf just goes away. The difficulty with this process is that the numerical treatment requires very small grid. When I say very small, it's between 100 meters and 1 kilometer. There is a theoretical point behind it. It has also been checked by intercomparison between models in 2D and in 3D. So you can imagine Antarctica is something like 3,000 kilometers, and you need grid of 1 kilometer. It's not possible just now. You have to find either a non-regular grid or strategies like adaptative grid. And now there are a few models that are able to do that. Okay. There is also a parameterization that is based on analytical solution, but this parameterization failed in simulating transient behavior at short time scale, so it cannot be used for the next century, for instance. So new generation of sophisticated model can deal with this process, and I will show you an example. This is Pine Island Glacier, which is a glacier that has been where we know the grounding line has retreated, and we have observation of that. This is a grid of the model. You see it's very small in the surrounding of the grounding line. The white line is a grounding line. Starting from the present situation and having a little bit more melting at the base makes the grounding line retreat. And this is after 20 years, then the grounding line is just at a very unstable point, and in 2 years it retreats a lot, and then it stops again around here. This simulation has been done with the two best models I know, and they get exactly the same results. So the conclusion is pig is likely to continue retreating. Even if the basal melting stops, you cannot make it advance again. Other regions could be affected by this process, and here is another simulation, not done with it's the same model. It is done with Grizzly, which is a coarser grid model, but where the grounding line can be forced to retreat to check where are the regions, and this is a probability to have a lowering of more than 100 meters. You recognize pig, but there is another glacier that is Thwaites, just beside, that is much more dangerous in terms of numbers, because the basin is much larger, and we don't know whether it will retreat or not. And you can see that the points I mentioned, Totten here, and the Wildland glaciers are also affected. The global estimation, there are a few simulations of the future, but I think really very little is -8 to 32 millimeters for the end of the century, including the change in surface mass balance. So these are the conclusions. The recent assessment has shown that the data about the estimation of present mass balance is much better than it used to be. For the Antarctic ice sheet, you see here, before 2012, we had a very increasing loss of mass. That is not at all in the present studies, because we corrected, people from this type of study corrected much better the uncertainty. But for Greenland, there is still an accelerating mass loss. And models have improved, but I think the marine instability is still the major unknown. It's not the unknown, but almost, especially concerning traits.